ahead and start. Good evening, everyone. Good morning, good afternoon, depending on where you're joining from. Welcome to the sixth day of the webinar series. We're very grateful to our sponsors, BioLens Laboratories, for sponsoring this event, and the Lens Ophthalmics as well. BioLens is a custom contact lens company that manufactures gas-fillable contact lenses, scleral lenses, orthokeratology lenses as well. And tomorrow, after the webinar, we'll be making an announcement for those who are interested and who meet the criteria for training in orthokeratology and multifocal contact lenses for myopia management. Today's topic is going to be one that's interesting and one that a lot of us do not typically consider in terms of measuring it clinically, but we know that it has some role in eye growth, erythropoiesis, and myopia. Our speaker for today is someone who's very well versed in the topic of myopia. He's a clinician scientist, currently undergoing his PhD at the L.V. Prasad Myopia Lab in collaboration with the City University of London. He's involved in both basic and translational research, and that research has led him to also co-develop a device that measures peripheral refraction clinically, and it's also a cost-effective device, which my research team has had the privilege of collaborating with the L.V. Prasad Myopia research team on using that device to measure peripheral refraction in African school-age children and young adults. So I introduced Swapnil Thakur, soon to be doctor when you complete it. So I'd allow you share your screen, and I'll stop sharing mine. You should be able to share your screen now. You can unmute your mic.
No, Ben, I think still.
Yeah, try now. Perfect.
So I'll just go to the slide showing.
That's okay.
Okay, so I welcome you again to yet another session of Myopia Awareness Week. And the topic for today is peripheral refraction, myopia development, and what is the role of peripheral refraction there. So interestingly, recently there has been recent interest among both clinicians and scientists about how peripheral refraction can alter the ocular growth. And this interest has resulted in the development of many devices, contact lenses, spectacles, which are meant to reduce the relative peripheral hyperopia, which is basically a hyperopic defocus, and that is known to control myopia. So one disclaimer is that this field is very evolving, and then few of the evidence is in a very initial phase. So that's the disclaimer before I start my presentation. So these are the outlines for my today's presentation. So we'll go through one by one. So first of all, we'll know about understanding about what is peripheral retina and how it plays a role in metropolization. Secondly, we'll know about understand about what is the concept of peripheral refraction, and thirdly, it will follow by to understand what is the level of evidence from the experiments done in animal species as well as in humans. Lastly, we'll understand what are the different techniques to perform peripheral refraction and how we can apply the concept of peripheral refraction in our clinics. So to begin with, let us just discuss about what is the role of visual experience and emmetroposition. From our previous knowledge, we already know that after the baby is born, the visual experience can decide on what is the level of refractive development it experiences. So from the evidence, it seems that whenever there is a hyperopic defocus, the eye tends to follow that defocus and it will elongate. And if there is a myopic defocus, the eye tends to shrink. So if you concentrate on the figure to the left right hand side, just ignore the top panel and focus on the fellow normal eye. So what happens during metropization is that due to the hyperopic correction, there will be an increase in the axial length. Along with the increase in axial length, there is decrease in the corneal curvature, increase in the vitreous chamber. So now if you focus on the feedback loop of the metropization, right? So the defocus is generally taken as a local processing. So that signals the metropization. So that is local processing. But since it's a metropization is a feedback loop, so it gets signals from the choroidal nerves, ciliary nerves, and then there is a accommodation role of accommodation. There is a lens change in the lens, change in the cornea, and then it modulates how much is the defocus in the visual system. Apart from this, we have another loop there in the upper portion where the sclera and the choroid also plays a role in the metropization process. But why I'm discussing this? Because the whole concept of metropization is primarily focused on the foveal region, which has received the much attention. But now what we are trying to focus today is peripheral retina. So if you focus on the top panel, that gives you the dimension of what is the different dimensions of the macula, periphobia, paraphobia, and fovea. So phobia is usually defined as 1.5 mm of diameter circle. Paraphobia is 2.5, and the whole macula is 5.5. Now this is the central portion of the retina, which which consists of only 3% of the total retina, the macula. But what is peripheral retina? So uh, when we go by the different classification given by Duke Elder book, so there are four zones how we can divide peripheral retina. So now if you focus on the figure in the bottom side, so the shaded area is the macula. How after macula there is near periphery. So 1.5 from the macula, it's the near periphery. And then we add if additional 1.5, which is 3 mm from the macula, which is mid periphery. So there is a portion called near periphery and the mid periphery. And after mid periphery, when we go 9 to 10 mm in the temporal, which will be far periphery. And if we go 16 mm nasal, that will be far periphery. Now, if we add zero point 0.2 mm from the far periphery, it's the extreme periphery. So from this figure, we can consider that the macula is only 3% of the whole retina, and the major part is the peripheral retina. Which brings us to the notice that since it's belong to the major part, it play an important role in refractive development. So when we compare central retina and the peripheral retina, there are multiple things which can vary among them. So this is if you focus on this figure, the central macula will have a high contrast visual acuity. But as we go from the center to the periphery, the retinal image quality decreases. Apart from this, since there are the number of cones drastically decreases from the center to the periphery, there is a decline in a spatial resolution. The density of ganglion cell increases from the center to the periphery. When we go from center to periphery, there is difference in the retinal circuit and other microstructural differences are there. But what is important to note here is that in the peripheral retina, the defocus is too much in comparison to center. So how the visual system is able to detect the defocus signals and then regulate the ocular growth. So there was one experiment done in chickens by Scafell and Diether in 1999. So they gave four conditions, which is uncovered eye, frosted occluder, 11.5 diopter of defocus, and 12.5 diopter of defocus. And the conclusion from this experiment was that even in the presence of poor image quality, the eye was able to detect the defocus signal, and then it was able to regulate the ocular growth. So given that now we understand about the importance of peripheral retina and then how it can modulate the refractive error development, let us just go through what is peripheral refraction. Peripheral refraction is nothing but refractive error in the non-foveal zone. And if you focus on the right hand side figure, let's bottom figure. So in a case of a myope where the rays are focusing in front of the retina, we usually tends to see a relative peripheral hyperopia where the rays are focusing behind the retina in the peripheral portion. The opposite is true for the hyperopes, where the central rays are focused behind the retina. However, the rays in the periphery are focused in front of the retina. And similar for the emmetropes. But how do we define peripheral refraction? If we do, let's say, retinoscopy at 5 degree, that is peripheral refraction. If we do retinoscopy at 10 degree, 30 degree. So what actually is peripheral refraction, we will know later. The other thing which is not clear from the evidence is that how much is the difference between center to periphery is actually we can define it as either RP relative peripheral hyperopia or relative peripheral myopia. So I'll go through one of the example here. So this is an illustrative example. Let's say in the right eye we have minus 2.25 diopter of correction, and left eye it has minus 9.75 diopters. While we do refraction at nasal 30 degree and temporal 30 degree. So let us only focus on temporal 30 degree. In the case of right eye, if the central portion is 2.25 and the temporal portion is minus 3.75, then it is indication that it's a relative peripheral myopia, which is of 1.50 diopters. In the case of a left eye, where the central portion, central refraction is minus 9.75, but the temporal refraction is minus 7.25. And this is an indication of relative peripheral hyperopia of 2.5 diopter. So this is a general uh, illustration of how we record peripheral refraction there. But the concept of peripheral refraction is not very new. It was very old. 40, 50 years back, there is two foundational studies done by Remt and Hugerheide, who performed peripheral retinoscopy on a pilot students who came for the aero examinations. So what was the findings of REMT? So what he did was he recruited 442 participants. Those participants were the person applying for the aeromedical exam, and they perform peripheral refraction using retinoscopy. So this was done, but before this study, there were other scientists such as Ferry, Rand, and Hardy, which has also tried to evaluate what is the peripheral refraction. But with the instrument, what they have used was, which is parallax refractometer, which was very cumbersome to use. So a simplistic technique was the retinoscopy, he performed the peripheral refraction. The outcomes of the REMT was he identified five patterns of relative peripheral refraction. So in the first pattern, uh, so this is your both horizontal and vertical meridian is in the hyperopic direction. In the second part, both the horizontal and the vertical meridian again in the hyperopic part. So there is two parts. So the top part, the H1 is the hyperopic side, the M1 is the myopic side. So in the third type of pattern, the horizontal meridian will have both the sides to the showed relative peripheral hyperopia, whereas in the vertical meridian, one side showed relative peripheral myopia, while the other side showed relative peripheral hyperopia. So, using all this technique, he has given us five possible patterns of relative peripheral refraction. So, after Remt has done peripheral retinoscopy with and gave five different patterns, after that his colleague Hugerheid uh, extended the findings of this Remt and then measured the peripheral refraction in 222 commercial pilots and 153 fighter pilots. So what he did was he was observing which of the pilots are developing myopia and what actually the relative peripheral refraction pattern they have. So what Hoogerheit observed is that majority of the pilot who showed myopic shift had type 1 refractive error pattern where both the meridian has relative peripheral hyperopia, which is 65% of the participant. What he also observed is that the majority of the participant also had the type 4 pattern, which is relative peripheral hyperopia along the vertical meridian, but relative peripheral myopia along the horizontal meridian, which was 58%. So from this, the whole concept of whether the peripheral refraction is important for myopia begins from here, where he reported that the pilots who became myopic had relative peripheral hyperopia. But recently, the findings of Hoogerheid was criticized because we don't know, it was not clear actually at what visit he did perform the peripheral refraction. So after the initial findings from Hoogerheid and Remt, there was a gap of 30-40 years. We didn't have any information about the peripheral refraction and its role in myopia. However, after 40 years, there were series of animal experiments which has demonstrated that how peripheral refraction or peripheral retina is important for refractive development. So the first category of the experiment where they give defocus signals in either chicks or rhesus monkey were the popular animal models at that time. So after giving defocus signals, what they observed is that the negative lens promoted the ocular growth in the animal species, while the positive lenses inhibited the ocular growth. The other category of animal experiment was optic nerve section. As a part of this experiment, they recruited guinea pigs and they cut the optic nerve of the eye. So the reason for doing this was that given that the optic nerve is removed from the eye, there is no connection of central nervous system. So whatever defocus signal or this growth signal is coming, that is coming from the peripheral retina. So the outcomes of this optic nerve section is is that when the optic nerve section was there, even at that period, the eye continues to emmetropize. So, the outcomes of this experiment concluded that the central nervous system is not required for the emmetropization, and it's the local signal from the peripheral retina which is important. The another landmark experiment which was done by Smith et al. What he did was he ablated the central 10 to 12 degree of, he performed the central 10 to 12 degree of foveal ablation, and then tried to see what is the ocular growth there. So the findings of this experiments have observed is that even though the
Please
phobia,
mute your mic, everyone. Please mute your mic.
even though the phobia was ablated, the eye continued to detect the defocus signal, and then it continued to emmetropize. So this was the three different categories of the experiment. See, the another category of experiment.
Papni, just give me a minute. I'll just reclaim host and mute this person.
Oben, can I reshare?
Yeah, 1 minute. You're going to reshare soon. Yes, you may reshare now.
Okay, is my slides visible, Oben?
Yes, it is. Sorry about that.
Okay, let me just try 1 second. Okay. So lastly, the another experiment was done where the defocus signal was only given to uh, one part of the retina and not the other part of the retina. And the outcome of these experiments have indicated that when the defocus signal is given to one part of the retina and not to the other, the eye elongation happens only at that part of the eye and not the other. So the outcomes clearly indicates from this experiment is that the peripheral defocus signals from the retina is basically local and not central. So after there are series of experiments done in various animal models, there was a period where the role of peripheral refraction started to be investigated in humans. One of the first study which was done by Mutti et al. On the role of relative peripheral refraction, how it changes the axial length, and they also the focus of this study was that they measured the relative peripheral refraction before the onset of myopia and after the onset of myopia. So if you look at this graph, so the x-axis, the numbers indicates the visit. So the zero visit is the onset of myopia, and -1, -2, -3, -4, and -5 are before the onset of myopia, and then subsequently the 1, 2, 3, and 4 and 5 are the after the onset of myopia. The white circle are the ones who had emmetropia all the over the visit, and the black square are the data from the participant who became myopic. Now the y-axis is your relative peripheral refraction. So if you carefully focus on this graph, the black square, even before the onset of myopia, if you notice that the person who has become myopic, there was a relative peripheral hyperopia. So it started to increase, and then at peak, when the myopia onset was there, the relative peripheral hyperopia was at peak. When you compare the person who remained emmetropic, there was no change in the relative peripheral refraction there. So from this was one of the landmark paper which concluded that the children who became myopic had hyperopic relative peripheral refractive error even before the 2 years of onset of myopia. And the other outcome of this study was that there was fast change in the refractive error, axial length, and relative peripheral refractive error before the onset of myopia. So this study gives an indication that relative peripheral hyperopia might be a cause rather than an association. But we should not conclude by looking at only the findings of this study. So what I did was I just ran a quick search on how many papers are there on relative peripheral refraction. So I did a basic search on Scopus using Embase database. And what I found was in total there was 96 articles which somehow somewhere investigated the role of peripheral refraction. So what I have tried here is that I have grouped a few of the articles which supported the theory of peripheral refraction and a different group where a group of studies which do not support the your peripheral refraction theory. So if you see this Venn diagram, the blue portion of the Venn diagram, you see that there are lots of study which have supported that there is a role of relative peripheral refraction there. So I have just quoted few of the key findings from those studies. So let's say the first study has indicated that in the HAL users, the SLR myopia control glasses, if the users are wearing those glasses, there is a uh, change in the steeper retinal curvature, and then retina is becoming steeper after wearing those myopia control glasses. After there are studies on MiSight lenses, which also indicates that wearing MiSight contact lenses can also results in change in the relative peripheral refraction. There are studies which says that the astigmatism is related to relative peripheral refraction. One of these studies have investigated that the child who were implanted with IOL, and but when they did relative peripheral refraction, they found that the child who had relative peripheral myopia showed less myopic shift compared to those child who had relative peripheral hyperopia. There are several of papers which has indicated that the wearing of ortho-K lenses could change the retinal curvature. Interestingly, apart from the optical strategy, there are few studies which has indicated that even the pharmaceutical myopia control agents could alter the relative peripheral refraction. I will discuss a few of those papers. And what other things we can know from this study was that the studies which has showed the role of relative peripheral refraction in myopia, they have concluded that the mid peripheral retina, which is 30 to 40 degree of in the visual field of the retina, is important for myopia. I will quote one of the findings from the DIMS glasses where they say that the nasal 20-degree relative peripheral refraction is more correlated with the DIMS efficacy. So from there, these when we collate these findings, we know that we have some consensus on that the mid peripheral retina is more important than the far retina. Apart from that, there are evidence to say that the ortho-K lens decentration induces relative peripheral myopia, and then that has some role there. So these were the few findings from the studies which has supported the role of peripheral refraction. However, we should not ignore those studies which did not show any which did not supported the role of peripheral refraction. So there were few studies which do not supported the role of peripheral refraction. One of the famous studies are outcomes from the Blink study, which reported that the relative peripheral hyperopia did not correlated with the relative peripheral eye length. So, in the animal studies, we have more consistent evidence, but in the humans, we have mixed evidence to say that whether relative peripheral hyperopia has any role in myopia or not. Yeah. So, what is wrong? So, why we are talking about relative peripheral refraction? So what is wrong with the single vision lenses? So if you focus on this bar chart, this is from an Indian data, which shows the practice pattern of how the clinicians are managing myopia. And interestingly, most of the clinicians are still prescribing single vision lenses there for or to manage myopia. But what is wrong with the single vision lenses is that if you focus on this right hand panel, if we give a single vision lenses due to the concave lens, there is if there is a relative peripheral hyperopia, then after single vision lenses, the magnitude of relative peripheral hyperopia increases. So clearly the single vision lenses is not going to work to elevate the defocus signals. So what is the desired way to control myopia? So basically what we want is that the central portion should be corrected. However, the peripheral rays now should focus, instead of focusing behind the retina, it should focus in front of the retina. So that's the desired outcome that we want. Okay, so what's new? So there are multiple myopia control strategy in the market which shows the efficacy of 50 to 70% of efficacy in controlling myopia progression as well as axial elongs. The most famous ones are SLR Stellus lenses and the Hoya MyoSmart lenses. So this, I'll just show you the video of how those lenses looks like. So in the right hand side, we see a more concentric ring for the HAL lenses. And the first video on the left hand side will show you how the pattern of defocus is there for the DIMS lenses. The one thing what I want to discuss here is that you will notice that the pattern of the lenslets which are there in both the spectacles are very much different. But the concept of both the spectacles are same, is to reduce the peripheral hyperopic defocus. So this was the evidence for how the optical strategy manages the relative peripheral hyperopic defocus. But there, interestingly, there are few studies which says that this low concentration atropine can also alter the relative peripheral refraction there. So one of the recent study by Tian et al., where they give 0.01% atropine for 1 year, it seems, and then they monitored how the relative peripheral refraction changes in comparison to the control line. So when you focus on this graph, the x-axis is your eccentricity. So 0 is the central, 15 is the 15 degree in the temporal, 30-degree temporal, 15-degree nasal, and 30-degree nasal. So if you focus on this graph, uh, if you follow the gray line, which is myopic children who were prescribed with atropine 0.01%, the relative peripheral hyperopia was bit less compared to the myopic children without the atropine 0.01% eye drop. So this was one of the first evidence to indicate that not only optical treatment, but also pharmaceutical myopia control strategy could alter the relative peripheral refraction. But this was very interesting because there in the optical treatment, we have hyperopic, we have lenslets there, which have myopic defocus, which reduces your hyperopic defocus. But in the pharmaceutical treatment, we don't have anything. But and therefore, we don't have a clear, concrete information about how this pharmaceutical treatment is altering the relative peripheral refraction. So similar to the first study, the another recent study have also reported that how 0.05% atropine could alter the relative peripheral refraction pattern. And there, the two graphs shows that the children who were prescribed with atropine, they had less relative peripheral hyperopia compared to the control group who did not used 0.05% atropine there. So what is the summary till now? So first point, what we have learned is that the peripheral retina covers the 97% of the whole retina and the macula only covers the 3%. So given that it covers the large surface area, the peripheral retina, therefore it can be an important, it should have an important role in myopia. The second point, what I want to indicate is that the visual system can utilize defocus signals in the peripheral retina, even in the presence of severely blurred image. The third point is what is peripheral refraction? Basically, it's a refractive error at non-foveal region. We also went through some of the foundational studies has which has created a foundation for the further studies to investigate what is the role of peripheral refraction. We have also seen that there are multiple experiments done in animal models where they have indicated that the mid periphery of the retina plays an important role for the myopia development. Not only animal studies, but evidence from the human studies also indicated that the 30 to 40 degrees of the mid peripheral region of the retina could be important for myopia. Lastly, but important thing to note is that not only optical treatment, but also pharmacological myopia control strategy can alter the peripheral refraction pattern. Okay, so the next thing what we want to know is that what are the different techniques to measure peripheral refraction. So I have divided the techniques into two parts. So the first is the clinic-based technique where we do peripheral refraction using retinoscopy. And the diagram displayed here is the spark, which is the non-electronic version, and the park. So I'll discuss the spark and park later. Apart from performing peripheral refraction with retinoscopy, we also have open field autorefractor. But the problem with open field autorefractor is that it requires a larger clinical space, and it's also very expensive. The other side of this story is that we also have some of the lab-based techniques where to measure peripheral refraction. But the problem with this lab-based technique is that the instrument is too large, or it's complicated, or it's still in the research field, and it's a little complicated to use in the clinical scenario. So given that we want to have some simple technique to assess the peripheral refraction, in collaboration with our engineering team at LVPI, we developed something called PARC. If I expand the PARC, it's a peripheral refraction using axillary retinoscopic component. So the Park was what it's an electronic version where it has three arms. So the central arm has its first central refraction. So basically, the Park has to be kept in the any of the trial lens rack of the trial frame, and then each arm has a light sensor. So if you see the extended arm on the right and the left, so that is aligned to a 22 degrees. So the purpose for those arms is that the moment the examiner throw the retinoscopy light at that arm, it will indicate you that now the examiner is aligned to 22 degrees and they can perform peripheral refraction. So we published this study in TVST in 2024, where we wanted to compare the peripheral refraction values obtained from retinoscopy and the peripheral refraction values obtained from your open field. And then while doing analysis, we found that in both temporal 22 degrees and nasal 22 degrees, there was comparable findings, what we obtained from the park with using retinoscopy and from the open field. Interesting finding, one of the interesting finding from our study was that the examiners were able to identify the relative peripheral hyperopia in 77% of the total participant along the nasal and the temporal merit, which is a good percentage. Apart from Park, we have a non-electronic version of Park, which is Park, and Obin and his colleague are doing a study on evaluating the relative peripheral refraction in Nigerian eyes, and the findings are very interesting. If you see this, the black follow this black line. This is the data from myopic eyes, and this clearly show that in the nasal meridian there is a relative peripheral hyperopia. However, in a non-myopic eye, there is a relative peripheral myopia. So from here, you can recall whatever we discussed earlier, that relative peripheral hyperopia is a risk factor for myopia development. So from here, it's consistent with our previous findings. So now we understood that uh, there are various techniques to measure peripheral refraction, and then the simplest one is using retinoscopy. So what next? If we do peripheral refraction, what should we do next? So there is something called impact myopia guideline, which it's a simple tool we can use in the clinic to evaluate or to tailor our management for myopia management. So impact stands, so the first letter of impact, which is I, the first step is to identify true axial myopia. The first step is to identify whether the patient has true axial myop and rule out the keratoconus, pseudomyopia, and other things where we don't want to initiate myopia management. Followed by identifying true axial myop, we want to assess the risk factor. And at this step itself, we want to do a peripheral refraction. If someone has relative peripheral hyperopia, we should consider that that individual might have a risk of myopia progression or myopia onset. In the third step, it's pick progressive myop, advise appropriate myopia control strategy. Again, this step is important to in our case, given that in our scenario, what we do generally is that if we notice someone with relative peripheral hyperopia, we tend to prescribe defocus lenses to them, because there are studies conducted in dim spectacles where they say that someone who have relative peripheral hyperopia at baseline, there they showed better efficacy with dims rather than someone who has relative peripheral hyperopia at relative peripheral myopia at baseline. So in that case, we want to give defocus lenses to only that individual who have relative peripheral hyperopia. After advising the appropriate myopia control strategy, we want to consult counsel and if required, combine the treatment. And the last step is to taper and when to stop the myopia control strategies. Apart from this impact guideline, we also have developed something called myopia progression risk predictor, where it's both for practitioner and for the patient. And then the purpose of this platform is to uh, have a quick screening of whether that patient have a higher risk of myopia progression or a lower risk of myopia progression. And there also, here we have one question where we indicate that is there a relative peripheral hyperopia in any of the meridian? If yes, the practitioner can mention the magnitude of the relative peripheral hyperopia which they have obtained from their refraction. And ultimately, based upon all the questions, it will give a report that whether that patient have low chance of myopia progression or high chance of myopia. So finally, I want to just give a clinical case example. So this is a clinical case example of an 11-year-old female where the PGP was in the right eye, it was minus 3.25 diopters. In the left eye, it was minus 3. On refraction, on the day of visit in the myopia clinic, she had minus 4.25, minus 0.50 cylinder at 170-degree axis. And in the left eye, it was minus 3.75, 0.75 at 180-degree axis. So there is clear progression in myopia. So what we wanted to do is to evaluate what is the status of the relative peripheral pattern. We performed refraction, relative peripheral refraction in that individual where if you note that there is a clear relative peripheral hyperopia in the in both temporal 30 degrees and in the nasal 30 degrees. So this made us to prescribe defocus lenses to that individual. If you focus on this graph, so the x-axis is the follow-up duration, y-axis is the refraction values. After we prescribe defocus lenses in the green zone, clearly there is a less myopia progression there. So from here, we can take one message is that we can tailor our treatment from what we have mapped in terms of the risk of myopia in that person. In this in this case, we consider that the relative peripheral hyperopia might be a risk for myopia progression, and therefore we went on to prescribe defocus lenses in this case. Okay, so this is my last slide. So this is the overall summary of what I have presented today. Is that peripheral retina is important, especially the mid-peripheral zone of the retina is important. The second is both optical and pharmacological myopia control options can control can alter the peripheral refraction in humans based on the current evidence. Peripheral retinoscopy can be an easy and cost-effective technique. And after we have evaluated the magnitude of relative peripheral hyperopia or myopia, we can use a simple step of impact guidelines to tailor our approach that should we prescribe defocus lenses or we should not prescribe. And lastly, each case we have to manage. Each case is different, and then we have to manage case by case. Okay, so lastly, I want to thank Owen for the invitation, and then I also want to acknowledge my myopia team, which have shared the information on peripheral fraction to me. Thank you. Owen, I think you are on mute. Yeah.
Thank you very much, Swapnil. That was really interesting. And I mean, I've been jotting down here. I mean, I know we're in the same team and we're studying peripheral refraction as well, but I have some questions to ask you. But before I do that, if you have questions, contributions, comments, drop them in the chat section. I know that the idea or the concept of peripheral refraction is not something that we all do in our day-to-day clinical practice, but it does form the basis for a lot of the myopia management options that we use. And if you have doubts, just leave them in the chat section and we'll take them. So there's a question here for you, Swapnil. The question is, kindly throw some light on refractive myopia in relation to myopia management. as well as peripheral refraction? Are we only concerned with axial length or axial myopia, basically?
So currently, I think we are more concerned about actual myopia, and we are not very not very concerned about the refractive myopia, because it's the axial length which grows, and then we tends to see a lattice and every retinal lesion. It's not refractive myopia which concerns us.
Yeah, I'll just add to that and say when we see refractive myopia, we would want to do corneal topography to rule out keratoconus or corneal ectasia, because it would not make sense to be managing a keratoconus patient, for example, with one of the myopia control strategies. If you were to do something like autokeratology for someone with keratoconus, the lenses won't fit properly. You
Yeah.
probably will alter corneal curvature and maybe cause keratoconus to even progress. So we're concerned when we refer to myopia management. We're talking about axial myopia, so just keep that in mind. So the next question is, um, okay, so I think this is referring to the PAC or SPAC. Where does the patient focus during peripheral refraction using a retinoscope?
For the park or spark, the patient is allowed to sit, the focus only centrally. They are not moving their eyes. It's the examiner who is moving. So basically, the two arm which I have showed you, it's the alignment confirmation of the examiner. The examiner should move at 22 degrees, and then once they throw light from the 22 degrees to the park or spark, they will see some light there. So that confirms that the examiner is now at 22 degrees, and they can perform refraction either in the nasal or in the temporal cavity.
Yeah, actually. So I mean it may not make I mean it may be confusing a bit if you haven't actually used the device, but it's basically performing your normal retinoscopy, but the device guides you on what angle you're at. So normally if you're doing your retinoscopy straight ahead, that's 0 degrees. So when you tilt 22 degrees to the left or 22 degrees to the right, the device has an indicator light on it that shows you you're on the right angle, and you just go ahead and perform your retinoscopy, subtract from the central values to get the peripheral refraction. So I have a question for you, Swapnil. So from the data we've collected and from data from Indian eyes and Caucasian eyes, um we see that there is asymmetry. So can you there is difference, ethnic difference seems to be there in terms of peripheral refraction. Can you speak about the ethnic differences in peripheral refraction?
Bin, thanks for the question. So the ethnic difference, I think it's there, but I think it's not very prominent because we don't have the data from multiple ethnicity. Let's say if I want to compare the Indian data with the Chinese, whatever has been reported in Chinese, it's more symmetric. And then we have noted that in the Indian eyes, we have more asymmetric peripheral refraction there. And interestingly, you also have noted that there is a asymmetric peripheral
Yeah.
refraction in the Nigerian eyes. Yeah, so we don't know even what really is the reason for the asymmetric peripheral refraction. Uh, what we want to assess is that we also want to do peripheral eye length just to correlate with the retinal shape with the peripheral refraction.
Yeah, and performing peripheral island, I mean, I understand that most of the devices that we have for biometry are all mostly central based, and I'm aware there are some papers that say when you use the central based biometers to measure peripheral islands, you might get some errors here and there. But how do you think you can maneuver that?
So, Oben, here we use is the goniometer, simple goniometer, where it's fixed in front of the lens star, and basically we rotate that goniometer, and it has a target at the end of the goniometer.
Mhm.
um, 5 to 10, 20 centimeter target there from the eye, and then patient can easily move their eye at that location, and then we can
Mhm.
perform the peripheral eye length. What is challenging for that for the peripheral eye length is that the variability is too much. So uh, so that we have to take care of.
Yeah.
So that is the only concern there.
And with this, I mean, the patient is moving the eyes, not the examiner moving the equipment, right?
Yes, patient moving their eyes.
Mhm. And considering that we see asymmetry, I mean, for at least African, Nigerian data and Indian data, we're seeing asymmetry between the nasal and temporal retina in terms of peripheral refraction. Do you think in future we might have myopia control devices that maybe might have an asymmetric sort of defocus incorporated into them?
Again, interesting question, Owen. I think I've read few of the papers which they are investigating how they can customize uh, the lenslets, the lens power in the temporal and the in the nasal side to just to have a different set of refraction there. So I think it's the future. I think few of the studies are developing those the asymmetrical lenslets.
So I'll check the chat section and see if we have more questions. Um, just a minute. Okay, it seems there are none for now. So I'd go to my next question. Um, I mean, there's something you did mention that takes me back to prescribing aphakic contact lenses for aphakic babies. And I remember several times when the kids come for follow-up and it's maybe time to assess the lens, you notice there's been a rapid increase in axial length, rapid increase
Yes.
in refractive error. And I mean, I do remember asking, this was back when I was in LVP, and I remember asking the consultant then why we didn't really have a reason. There was nothing concrete, but we know that we were doing the 3-2-1 rule where we would leave the kids slightly myopic. So we were causing a bit of myopic defocus. Shouldn't that have been protective for myopia because we were leaving them myopic? But we then see in kids or babies who had IOLs implanted from an early age, we're still seeing the axial length increase.
Yes.
And we theorize that that's due to peripheral refraction. But if we were leaving the aphakic babies myopic with the contact lenses we were fitting, why were we still seeing axial length increase?
Hmm. Often we don't have, at least I don't have the clear answer for this. Maybe
Yeah.
I think once it would be interesting from you guys to just when you fit those aphakic contact lenses, you if you can quickly assess that the what is the
Peripheral
how the
refraction.
reflex is changing with.
I mean, I think that would be an interesting study to do. I mean,
Yeah.
especially because you're in the setting where you could do refraction on that EUA, and that could be something that somebody could look at using the SPAC device, refraction on
Yeah.
the EUA, and then trying to see the differences between the contact lens corrected aphakic babies and the IOL corrected ones. So we probably would understand who would likely progress because sometimes
Yes.
jump you see and you might have a baby who you fit with contact lenses and they come back in 3 months' time and the contact lens is useless. So you have to get another one again. So it'd be nice to predict that and see. I see someone has, okay, Dr. Professor Bernardine, you want to say something? Your hands are up. Okay, so I think I need to unmute her, I think. 1 minute.
Okay, thank you very much.
Yes.
It was a very interesting presentation. I just wanted to have a clear cut how you would order the lens for the focus lens after you have done the refraction and you have done the peripheral. You had like -4 here and you had -3 here. So how would you now place the order for the lens for that? Is it going to just be exact the values you got? Or what? How do you place the order
So,
for that?
so Swapnil, you can go.
So if I understood, Oben, professor is asking that how we are prescribing those defocus lenses based
Yes,
Yes,
upon the
so
peripheral.
after
yes,
you measure peripheral refraction in an individual, say we find +1 relative peripheral hyperopia, how does that factor into your prescription of a defocus lens?
Professor, so we do actually we cannot actually alter the lenslets what's actually there in the defocus spectacles. So that's the limitation we currently have. What we are currently doing is that once we know that there is a relative peripheral hyperopia, we are likely to prescribe them either the defocus spectacles or the peripheral defocus contact lenses,
Yeah.
irrespective of what is the magnitude. So basically, the magnitude of peripheral refraction is till now only limited to research and not being very directly applied to the clinic. In clinic, we generally want to see that whether it's relative peripheral hyperopia or relative peripheral myopia.
Yeah, so I'll just add to that and say the reason is we don't have control of the plus powers that's put in the lenslets. For example, in the DIMS lens, it's the lenslets has +3.5. You cannot alter it as a practitioner, it's fixed. You can only alter the central power you're given for vision correction, not the plus power in the lenslets in the periphery. Same thing for Stellest, same thing for Myocare and other defocus lenses. The only place you might be able to customize is when you're prescribing center distance multifocal contact lenses. You can decide to customize the ad. However, this has not been studied. But from the Blink study, they had compared the low ad and the high ad and found out that children who they prescribed center distance multifocals with high ad, that's an ad of +2.5, had better myopia control compared to those who they prescribed low ad of +1.5. So the idea may not be you tailoring the focus correction to the peripheral refraction that you've identified, because at the end of the day, we actually want to overcorrect the peripheral hyperopia by inducing peripheral myopia to actually cause myopia control. So, but just like Swapnil said,
Can you say that again? It's something you just said now. Can you say it again?
okay, yeah. So I was saying that the idea for peripheral refraction and the way we use it for myopia control is not necessarily to tailor the change or the add or the plus power we give. We're actually trying to overcorrect the peripheral hyperopia to induce peripheral myopia. So let's say you have an individual who has peripheral hyperopia of +1, for example. And if you use the DIMS lens, for example, which is plus 3.5, that means you would have overcorrected by about 2.5. So in the periphery, you would be inducing about 2.5 diopters of myopia. So because you have induced peripheral myopia, the optical stimulus that makes the axial length go backwards is no longer there in the periphery. So the idea is actually to overcorrect the peripheral hyperopia. But what Swapnil is trying to say is in the clinics, we would use the peripheral refraction to help us determine who will likely benefit from a defocus option versus who may benefit from just a pharmaceutical option or maybe the contrast signaling lens like the dot lens. And instead of just prescribing defocus spectacles to everybody. So it might help you tailor your management to which patient will benefit from one management compared to the other.
Fantastic. Okay.
I mean, we're currently doing this in Nigerian kids, but we're just first of all trying to get, I mean, I presented the initial results at Academy, but we've got more data now. We're trying to just map out what is normal for myopic individual children, hyperopic children, and emetropic children. And then a further step will be probably looking at the intervention side of things. So maybe we might have answers to these questions in future.
Okay, thank you very much. I think it's clear now.
All right. All right. So I think that's as many questions as I have. I guess because we're on the same team, I'm not blasting you today. But thank you very much, Swapnil, for
Thank
doing
you
this, and
again.
thank you everyone for joining in. So remember to I sent the link for the iAfrica Media YouTube page. The recordings are available there. And for those of you who've sent emails to me or other people in the team, we'll be replying as soon as the webinar series is done, and then connect those of you who are interested in research, data collection, collaboration, learning about myopia management. And tomorrow after the webinar, so tomorrow's webinar is basically going to be on contact lenses for myopia management. And after which there'll be an announcement that will take from BioLens for individuals who are interested in orthokeratology training and who meet the criteria for it. But thank you everyone for joining in, and thank you Swapnil very much. I know it's really late, so you can go back to bed now. Thank you so much. All right. I just did you want to say something, Swapnil? Okay, I think he's off. All right, good night, everyone.